Okay, welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 5 from the June 2011 Mechanics 1 paper. That's from OCR examining board. And this has a code 4728. And this question, I have gone through it basically because I've added it to my end of topic worksheet for my Mechanics 1, which is for AS or A2, in fact, Cambridge. And this is the topic of momentum, which is a topic which was added in 2020 to the syllabus. So there's not that many questions as there are in other topics. So that's why I decided to take a few questions which are of a similar nature from other examining boards. So OCR questions are quite similar to the Cambridge questions in this topic. So that's the reason why I decided to take this question for purposes of giving some practice from other examining boards of similar style questions. So here we have question number 5, which is 7 on my worksheet. It says 3 particles P, Q, and R lie on a line of greatest slope of a smooth inclined plane. Okay, so a few little points. When it says lie on a line of greatest slope, if you imagine you're looking at the slope, okay, let's say we're looking at a slight angle, so we have just make it 3-dimensional. This is the slope that they're lying on. It's like P, Q, and R. They lie on a line which is basically, vertically upwards. It's not like at an angle. It's the line of greatest slope. It's not at an angle going like from one corner to the other. It's straight up, directly up. The shortest distance between there and there. That's what it means, basically, something like that. Of a smooth plane, so there's no friction involved. P has a mass of 0.5 kilograms, so that's 0.5 kilograms, and is initially at the foot of the plane. R has a mass of 0.3 kilograms and is at the top of the plane, and Q has a mass of 0.2 kilograms and is in between the two, P and R. Okay, as in this diagram, P is projected up the plane with a speed of 3 meters per second. Okay, whereas Q and R are initially released from rest. So both of these are released from rest in the beginning of their motion. Okay, so this is like when time equals 0. This is a situation where time equals 0. This is projected up the plane. These are at rest, but they're released from rest. Okay, so we're going to start moving down, those two. So each particle has an acceleration of 2.5 meters per second down the plane. So you're going to have an acceleration downwards of 2.5 meters per second squared. So 2.5 meters per second squared. So that's a situation right at the start of the problem here. So now it says P and Q collide 0.4 seconds after being set in motion. Immediately after the collision, Q moves up the plane with speed 3.2 meters per second. Find the speed and direction of motion of P immediately after the collision. So this is when time equals 0. So we got to find now what was happening to P and Q when time was 0.4 seconds. And that will be just before the collision. And then we can consider what happens after the collision by using conservation of momentum. So we have to first work out now what speed P and Q are moving at. What were their velocities just before the collision? So here for this, we can use SUVAT. So we know that the time that we're dealing with is 0.4 seconds. So we have to look at where we're considering what happens between 0 to 0.4 seconds for time. That's what we're considering. So let's consider P and let's consider Q and think about what we have. So I'm going to put SUVAT here because it's constant acceleration. Right? So SUVAT. Okay, now P is moving up the plane, so I'm going to take up as positive. Q is moving down the plane. For Q, I'm going to take down as positive. There's no problem if you can switch like that in these kind of situations, because I'm trying to find what happens to P and what happens to Q kind of like separately. So S is the distance that P moved up the plane, right? Which we don't know, of course, so I'll just call that SP. U is its initial speed, which we know is 3 meters per second up the plane, so it's positive 3 for us in this question. V is what we're trying to find, the velocity of P as after 0.4 seconds. The acceleration is downwards, down the plane of 2.5 meters per second squared. So in the case of P, I'll call it negative 2.5 meters per second squared, and the time, as we see, is 0.4 seconds. Let's put the information for S as well, and then we can work them out. So S, we don't know how far it's moved down the plane. Its initial speed was 0 because it was released from rest. We want to find the speed of Q after 0.4 seconds. Now, as it's accelerating down the plane, I'm taking down as positive for Q. The acceleration will be 2.5 meters per second squared, and the time again is 0.4 seconds. So now, if we look at what we have here, what we need to find is V for both of them, and we have U, A, and T as well. So we're looking to find these four. So we can see that we can use the equation V equals U plus A, T. So if we consider, for example, P, okay, we have V is VP equals U is 3 plus A is negative 2.5 times T, which is 0.4. Okay, so you have VP is equal to 3. Now that's minus 2.5 times, I think that's going to be minus 1. Okay, that's going to be minus 1. So the velocity of P is going to be 2 meters per second. Okay, and as we've taken up as positive, that's going up. It's going up the plane. All right, and for Q, we're going to have the velocity of Q, which is going to be, we're going to have V equals U, which is 0, plus 2, plus A, which is 2.5 and positive, times T, which is 0.4. So the velocity of Q is going to be 2.5 times 0.4, which is 1. So it's 1 meters per second. And for this, it's going to be going down the plane. Okay, we took down as positive for this. All right. So now let's look at the situation just before the collision. And we can look at the situation just after the collision. So just before the collision, P is moving up with the speed of 2 meters per second. And Q, that's P. Okay, that's P. And Q is moving down with the speed of 1 meters per second. Okay, that's Q. And the mass of P was, as they told us, 0.5, and the mass of Q was 0.2. Okay, that's 0.5 and 0.2 here. So 0.5 kilograms and 0.2 kilograms. Okay, kg. And after the collision, they've told us that immediately after the collision, Q moves up the plane with speed 3.2 meters per second. So after the collision, Q is moving up the plane with the speed of 3.2 meters per second. And we have to find the speed and direction of motion of P immediately after the collision. So we need to find what VP is after the collision. So this is before, okay? This is before and this is after. So now what we can do is we can use the conservation of linear momentum. So the total momentum before the collision, and what I'll do is I'll take up the plane as positive, right? So the total momentum before the collision would be the mass, which is 0.5 times the velocity, which is 2, plus, and then we're going to have the mass of Q, which is 0.2 times its velocity, which is 1. I'll take that as minus 1 as I'm taking up as positive here. And that's equal to the total, the total momentum after the collision. So we consider afterwards. So we have 0.5 times VP, which we have to find. And we got plus, and you got 0.2 times 3.2, which will be positive because it's going up the plane. So the only unknown here is VP. So we have 0.5 times 2, which is 1, minus 0.2 equals 0.5 times VP. And you're going to have 0.2 times 3.2, which is going to be plus 0.64. Okay. So we have 0.8 equals 0.5 times VP plus 0.64. So we end up with 0.8 minus 0.64, 0.8 minus 0.64 divided by 0.5 equals VP. So that's basically going to be VP equals 2 times, because if you divide by half, multiply by 2, 0.8 minus 0.64 is going to be 0.16. So you end up with 2 times 0.16, which is going to give you 0.32 actually, 0.32 meters per second. 0.32 meters per second. And it's a positive answer, so it's going to be up the plane. Up the plane. Okay, we're taking up the plane as positive. Let's find the speed and direction. So we can say the speed is 0.32 meters per second, and it's going up the plane, Okay, so there's the answer to part 1 of the question. All right, so that's pretty straightforward. So we had to work out, I mean, the mistake people might have made is taking 3 and 0 as the speeds just before the collision, but that's not the case, right? If it was a horizontal plane, then yes, because it's frictionless, that would continue at the same velocity until it hits Q. However, it's a plane which is inclined, so there's a deceleration, okay, for this one, and this will accelerate towards this will go slower as it reaches it. So at the point where they collide, that won't be their speeds. So the speed before the collision will be the speed at the point at which they collide, which is 0.4 seconds into their journey. That's why we have to consider that. So there's the part 1. Now for part 2, it says 0.6 seconds after its collision with P, Q collides with R, and the two particles coalesce. Find the speed and direction of motion of the combined particle immediately after the collision. So now for P, we got to consider what happens between time equals 0.4 to 0.6 seconds. Okay, so what's happened to P is Q, not P, Q. So after Q has collided with P, if we go here and see, so P has collided with Q. Q is now going up the plane, okay, with a speed of, as they told us, 3.2 meters per second. Okay, so after the collision, Q is moving up the plane now. Okay, Q is moving up the plane, okay, with a speed of 3.2 meters per second. That's the speed of Q as it goes up the plane. All right. This is Q, and it has a mass of 0.2 kilograms. Okay, so that's 0.2 kilograms. Now R basically is released from rest. Okay, now see, for R it's like going to be between t equals 0 to 0.6 seconds. Okay, because what's happened with R is it's got 0.4 seconds, and then it says, okay, actually this is going to be basically, this will be moving for 0.6 seconds. We're going to see what happens to this, 0.6 seconds after the collision. For R, the time is going to be 1 second, because it's going to be 0.6 plus 0.4. So 0.4 was the time that it was moving after it was released. Because if you read the question again, R was released at the same time as Q. So R has been moving for 0.4 seconds, and then another 0.6 seconds when it collides with Q. So totally, R has been moving for 1 second. 0.4 plus 0.6 seconds at the time when it collides with Q. Okay, so we're going to consider the time for R as 1 second, okay, to find its speed when it hits Q. Both of them are accelerating down at 2.5 meters per second squared. All right, and here its initial speed was 0 meters per second at the time that it was released at 0 seconds. That was released. Okay, so that's R, and R has a mass of 0.3. Let's just make sure of that. R has a mass of 0.3 kilograms. Okay, so now we're going to consider, again, for P, I'm going to consider between, it says, okay, for the time as a 0.6 seconds, okay, that's 0.6 seconds after it was released. After 0.6 seconds after it hit P, and it started moving upwards. So we can look at what we have here, S, U, V, A, and T. So S is the distance it moves, I don't know. U is 3.2 up the plane. I'm going to take up the plane as positive because it's moving up. V is going to be VP, which I want to find now. The speed with which it hit R. And A is negative 2.5, and the time now is 0.6 seconds. Okay, and for Q, I'm going to take down as positive as it's moving down. Okay, and I'm going to take the time as 1 second to find the time from when it was released until it hit Q. So it has to be moving for 1 second altogether, right? With that same motion. Okay, so we have here S, U, V, A, T. So S is going to be the distance Q moves. Sorry, this is now R, not Q. I've got the labels wrong. This is Q, and this is R. Sorry about that. So this is SR, and this is S. This is SQ. Yes, I'll write that right. SQ. This is SR now. Okay, sorry about that confusion there. Now, its initial speed was 0. Its final speed is what I want to find. VR is acceleration. It's going down, and the acceleration is down, so I'll keep that as positive 2.5, and it's been moving for 1 second until it collides with Q. So now we can again use the same formula, V equals U plus AT. So for Q, we have VQ is equal to U, which is 3.2, plus A, which is minus 2.5, times T, which is 0.6. And for R, we have the velocity of R is equal to U, which is 0 plus 2.5 times 1. So the velocity of R is 2.5 meters per second, okay, going this way before the collision. And Q is going to be 3.2 minus 2.5 times 0.6. Okay, so the calculator, we have 3.2 plus 2.5. Okay, that should be brackets minus 2.5 times 0.6. Okay, and that gives us 1.7 meters per second. So VQ is 1.7 meters per second, and that's going up. Okay, that's going up and that's going down. So now they've told us after these two will collide, and these are the speeds at the point where they collide, which is 0.6 seconds after the collision of Q and P. But after they collide, okay, we want to find the speed and direction of the combined particles. They coalesce and become like one particle together with the combined mass. So we can see what happens before and after the collision. So we can think about before the collision, their speeds, and after the collision, their speeds. So you have 0.2 kilograms and 0.3 kilograms as their masses. So this is Q and this is R. So 0.2 and 0.3. The speed before is 1.7 this way. The speed before is 2.5 this way. And after the collision, they're like one combined mass of 0.5. And we want to find what the velocity of that combined mass is. Okay, so we can now work that out. We'll just call this V. Just call it just V. Right, we can work out that velocity by using the conservation of linear momentum again. So if I take this direction as positive again, we can then say, okay, 0.2 times 1.7 plus 0.3 times minus 2.5. Okay, was that 2.5? Yes, 2.5 is equal to the total mass, which is 0.5 times V. Okay, so now we have to basically take all this and divide it by 0.5. All right, so we're going to take 0.2 times 1.7 plus 0.3 times negative 2.5 and divide this by 0.5. Hold on. Let's do this first. And divide all of this by 0.5. Multiplying by 2 gives you minus 41 over 50, which is negative 0.82. So we can say the velocity of the combined particle is negative 0.82 meters per second, which means, as we took up as positive, it means that the speed of the particle, the speed of the combined coalesced particle, the speed, okay, is 0.82, meters per second. So the speed is, we give it as a magnitude. We don't give it with the direction. We don't mention negative or positive for the speed. 0.82 meters per second. But they say, and the direction, the question says find the speed and direction of motion. So as we have taken up as positive, it's going to be moving down the plane. Okay, so it's going to be, its direction is down the plane. Down the plane. Okay, it's going in this direction because we took up as positive and it's a negative answer. So there's the answer to question number 5 from my number 5. Oops, this is the wrong question. This one. What am I doing here? Yeah, this is question number 5 from this worksheet. Okay, or from this paper, June 2011 M1 paper, and this is also question number 7 for my end of topic worksheet. Okay, that completes this whole question. Other questions from this particular paper. This June 2011 paper can be found in the playlist that will be appearing at the top right of the screen at the end of the video. Other questions from the end of topic worksheet on momentum from this Cambridge collection will be found in the playlist over here. You'll find other questions from momentum and impulse of Cambridge of Edexcel questions. I'll put in the playlist over here because there's a lot more questions I've done from the Edexcel syllabus, and some of them are kind of similar. So I'll put the playlist for that here, so you can have a look at some of those examples, and you can subscribe to my channel by clicking on this link. Thank you for watching, and see you soon.